In a continuing effort to secure an ongoing supply of clean water to meet the escalating need for drinking water, sanitation, irrigation and industrial water uses, we need to adopt an improved level of sustainable practices. An overall increase in the practice of desalination and wastewater treatment for the regeneration and extraction of clean water is becoming more compelling. As we extract an increased volume of clean water from the streams of available water sources, the remaining mixed concentrate solutions, commonly referred to as brines, become more highly concentrated. These brine concentrates typically contain a mix of mineral salts and trace or heavy metal residues. The trace residues may contain any random assorted mix of rare earths, precious metals, minor and base metals and a blend of strategic minerals and other elements, and are ideal for the Recovery 2.0 concentration and selective extraction process. While the mineral salts are limited to a complex mix of alkali metals and alkaline earth elements. In Group 1 of the periodic table, we find lithium, sodium, potassium, rubidium, cesium, and francium. While in Group 2 we see beryllium, magnesium, calcium, strontium, barium, and radium. When we look at an example of seawater which starts out with a content of about 3.5% salts, after the desalination process the brine discharge has increased to approximately a 7% mineral salts concentration. The mineral salts will begin to crystallize or precipitate and drop out of solution at about a 20% saturation point. But the mix of mineral salts do not all come out of solution at the same time. As brine evaporates, minerals precipitate in the reverse order of their solubility, with the least soluble minerals forming first. The sequence for typical brine that first releases the calcium content materials including carbonate minerals such as calcite and dolomite are the first to form, and then the sulfate minerals such as gypsum and anhydrite precipitate next. Then the halides, such as sodium chloride which is common table salt, which typically yields the most abundant recovered evaporated mineral by volume, crystallize when the solution is reduced and reaches about 10% of the original water volume. Potassium and magnesium salts such as potash and other various highly soluble salts such as sylvite, carnallite, and polyhalite form last, in the final stages of evaporation that occurs with around 4% of the original water volume remaining. The precise sequence can be influenced by local factors like temperature and the specific chemistry of the original input water, which can result in the formation of other specific minerals like trona or borax. Lithium is among the last element to precipitate as a mineral during brine evaporation, not concentrating in the residual solution until very late stages. This high solubility of lithium chloride allows it to remain in a concentrated liquid form after most other common salts have crystallized out. Direct lithium extraction, known as DLE, is an alternative option for the selective lithium capture from the brine as it passes through a DLE system. This system uses specialized materials, like resins or solvents, to selectively grab a hold of the lithium ions. In summary, the mineral salts may be recovered in a responsible and sustainable fashion, converting residual residues into a valued resource. Recovery 2.0 is a project developed by Waste.net. Please feel free to visit us today at www.waste.net.